Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss some important compounds of carbon and silicon. Last class I have discussed allotrope of carbon. In that I have discussed about diamond, graphite and fullerenes. Now I am going to discuss some important compounds of carbon and silicon. Two important oxides of carbon are carbon monoxide and carbon dioxide. Come to the carbon monoxide. Direct oxidation of carbon in limited supply of oxygen or air yields carbon monoxide. That oxygen or air should be in a limited, very less. Then carbon plus oxygen means oxygen is less, carbon is more, 2C plus O2. On heating, it forms 2CO, carbon monoxide gas. On a small scale, pure carbon monoxide is prepared by dehydration of formic acid with concentrated H2SO4 at 373 Kelvin, means 100 degree centigrade. Formic acid HCOOH, when it is heated in presence of H2SO4, then it forms two products, carbon monoxide plus H2O. This is a laboratory we can make by this method in less quantity on a small scale. But on a large scale, on commercial scale, it is prepared by the passage of steam over hot coke. The mixture of CO and H2 thus produced is known as water gas or synthesis gas. It forms a mixture of carbon monoxide and hydrogen, and this is called water gas or synthesis gas. Means C, carbon solid plus H2O, means it is a steam, gaseous form. At 473, between 473 to 1273 Kelvin, in this range, if it is heated, then it forms carbon monoxide gas plus H2 gas, means hydrogen gas, and this mixture is known water gas. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. Both gases is asked in examination. When air is used instead of steam, then a mixture of CO and N2 is produced, which is called producer gas. Means 2C plus O2 plus 4N2, because in air oxygen and nitrogen both are present. Hence 2C plus O2 plus 4N2 at 1273 Kelvin, it forms 2CO plus 4N2. Okay. This is called producer gas. Water gas and producer gas are very important industrial fuels. Here I want to tell you 2C plus O2 plus 4N2. Here 4N2 is there, and in product also we are getting 4N2. Means product we are getting 2CO plus 4N2. Then 4N2 is common. Then what is the use of 4N2? In your mind it may come. 2C plus O2 plus 4N2. it is giving 2CO plus 4N2. Then here you are using air, and in air nitrogen gas is present. Then this oxygen of air plus 2C, it will form carbon monoxide, and nitrogen will not react with carbon, only it will be present with product, and that gas mixture is known as producer gas, means mixture of CO plus N2. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas, also called producer gas, can undergo here carbon monoxide in water. Carbon monoxide in water gas or producer gas can undergo further combination, forming carbon dioxide with the liberation of heat. Carbon monoxide is a colorless gas, colorless and odorless gas, and almost water insoluble gas. It does not dissolve in water. It is a powerful reducing agent, means it can supply the electron. It is a powerful reducing agent and reduces almost all metal oxides other than those of the alkali and alkaline earth metal, means group 1 and group 2. It will not react. Other metal oxide, it will convert to metal. Then again I am telling you that it is a powerful reducing agent and reduces alkali. It reduces almost all metal oxides other than those of the alkali and alkaline earth metals, and aluminum and a few transition metals. Some exception is there. It will react with all oxides and it will convert from oxide to metal. This property of CO is used in the extraction of many metals from their oxides. Okay. During extraction time, it is used, metal oxide is converted into metals, okay, from their oxides. Example, Fe2O3. Fe2O3 is a solid plus 3CO. It forms, on heating it forms iron plus carbon dioxide gas. Then ferrous, Fe2O3, it is oxide of ferrous. Now it is converting to ferrous. Fe, iron. Fe2O3 plus 3CO, it is converting into 2Fe, solid, plus 3CO2 gas. Other example, zinc oxide, ZnO, solid. It will react with carbon monoxide, means CO. On heating, it gives Zn solid plus CO2 gas. In CO molecule, there are 1 sigma and 2 pi bonds. C and O, 3 bonds are there. Between C and O, 3 bonds are there. Then there are 1 sigma and 2 pi bonds between carbon and oxygen. Because of the presence of a lone pair of electron on carbon, CO molecules act as a donor and react with certain metals when heated to form metal carbonyl. If you will see the structure of CO, then you will find that this C and O triple bond is there. Then on carbon 2 electron is there, 1 pair, and oxygen also 1 pair electron is there. Then This one pair electron on carbon plays a big role. Means the CO molecules act as a donor due to that one pair of electron on carbon. CO molecules act as a donor and react with certain metals when heated to form metal carbonyls. It will form metal carbonyls. The highly poisonous nature of CO, carbon monoxide is a highly poisonous gas, always remember. The highly poisonous nature of CO arises because of its ability to form a complex with hemoglobin. It reacts with hemoglobin, means from the blood. In blood, hemoglobin will be there. Iron. Then it forms complex with hemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. Oxygen also forms a complex with hemoglobin, but carbon monoxide also forms. But this carbon monoxide complex with hemoglobin is 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen round the body and ultimately resulting in death. This is a very, very important reaction. This you can say carbon monoxide forms complex with hemoglobin, and which is 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen round the body and ultimately resulting in death. Now I am going to discuss carbon dioxide. Carbon dioxide is prepared by complete combustion of carbon and carbon containing fuels in excess of air. C plus O2, it forms a CO2 gas. This is very common reaction. C plus O2, it forms a CO2 gas. CH4 plus 2O2, CH4 plus 2O2, it forms a CO2 plus 2H2O gas. Okay, both are in gaseous state. Vapor means 2H2O means vapor. Then CH4 plus 2O2, it forms CO2 gas plus 2H2O. In the laboratory, it is conveniently prepared by the action of dilute HCl on calcium carbonate. CaCO3 plus 2HCl, it is formed CaCl2 aqueous solution. It is in aqueous solution plus CO2 plus H2O. This is again very important and lab method to prepare carbon dioxide. CaCO3 plus 2HCl, it is forming CaCl2 plus CO2 plus H2O. On commercial scale, it is obtained by heating limestone, that is the calcium carbonate. It is a colorless and odorless gas. Its low solubility in water makes it of immense biochemical and geochemical importance. Okay, this because it is low solubility in water. In water, it will not dissolve. That is very, very helpful. Okay, and its low solubility in water makes it immense biochemical and geochemical importance. With water, it forms carbonic acid. CO2 plus H2O, it forms H2CO3, that is called carbonic acid, which is a big dibasic acid. and dissociate into two steps. This carbonic acid will dissociate in two steps. First step, that is H2CO3 plus H2O. It forms a bicarbonate HCO3 1 minus plus H3O hydronium ion. H2CO3 plus H2O, it forms a HCO3 1 minus plus hydronium ion. Hydronium ion H3O. HCO3 plus H2O. Second step, HCO3 plus H2O, it forms carbonate CO3 2 minus plus H2O. Then these two step reactions are there, that H2CO3 converts to bicarbonate and bicarbonate converts to carbonate. Then H2CO3 means carbonic acid, or you can take bicarbonate buffer system. HCO3 is converting to the H2CO3 is converting to the bicarbonate buffer system, helps to maintain pH of blood between 7.26 to 7.42. Question is asked. Due to this buffer system, means H2CO3 converts to bicarbonate. Then this is means H2CO3 HCO3 buffer system helps to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, CO2 is acidic in nature, remember. Being acidic in nature, it combines with alkalis to form metal carbonate. Carbon dioxide, which is normally present in the air in the extent of 0.03% approximately by volume in the atmosphere, is removed from it. How? From the atmosphere, carbon dioxide is removed. How? Then in a natural way. It is removed from atmosphere by the process known as photosynthesis. It is the process by which green plants convert atmospheric CO2 into carbohydrates such as glucose. Okay, this is very, very important, photosynthesis. In this process, carbon dioxide from air is removed or is absorbed, and it is in the presence of sunlight and chlorophyll. Chlorophyll is found in the plant. Then in the presence of chlorophyll and sunlight, carbon dioxide is converted to glucose. Okay, the overall chemical change, you can write like this, very important reaction, 6 CO2 plus 12 H2O. Moisture is also required. Carbon dioxide plus moisture plus sunlight plus chlorophyll, 4 things are required. Sunlight means H nu, you can tell. H nu, ultraviolet light. Then 6 CO2 plus 12 H2O, it forms a 3 product. It will give you glucose, means 6 C6H12O6 plus 6O2 plus 6H2O. Then H2O, 12 H2O it is used, but 6 H2O you are getting back. Means only 6 H2O you are going to use. Okay. Then this is the balanced equation, 6 CO2 plus 12 H2O. In the presence of chlorophyll and H nu, you can tell, or ultraviolet, it gives C6H12O6 plus 6O2 plus 6H2O. By this process, plants make food for themselves as well as for animals and human beings. Unlike CO2, unlike CO, carbon monoxide, It is a non-poisonous gas. It is not poisonous. It is a non-poisonous gas. But the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture in recent years seem to increase the CO2 content of the atmosphere. And if in atmosphere CO2 content will increase, quantity of CO2 will increase, then this may lead to increase in greenhouse effect because it absorbs the heat. Carbon dioxide absorbs the heat, or wherever carbon dioxide will be there, during the process heat is evolved. Also you can tell carbon dioxide means heat will be always, it is a exothermic reaction. Heat will be produced, or you can tell with carbon dioxide. If carbon dioxide will increase, it means heat will increase. Then that is called greenhouse effect, and thus raise the temperature of the atmosphere, which might have serious consequence. This is not good. Carbon dioxide can be obtained as a solid in the form of dry ice. Solid carbon dioxide is called dry ice. How will you get? Then by cooling it. Carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied carbon dioxide to expand rapidly. Dry ice is used. Dry ice is solid carbon dioxide, don't forget. Dry ice is used as a refrigerant, means a cooling agent, coolant. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous carbon dioxide is extensively used in carbonated soft drink. Cold drink, always you might be drinking cold drink. Then carbon dioxide is filled in the bottle at high pressure. That's why when you will open it, then some bubbles will come, gas will come. Then there it is used, carbon dioxide is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. In fire extinguisher also it is used. A substantial amount of carbon dioxide is used to manufacture urea, CONH2, NH2. Then urea is used as a fertilizer. In CO2 molecules, carbon atom undergoes sp hybridization. Again important things I am telling you, question is asked. In CO2 molecules, carbon atom undergoes sp hybridization. Two sp hybridized orbitals of carbon atom overlap with two p orbitals of oxygen. Carbon and oxygen both will react. Then two sp hybridized orbitals of carbon atom overlap with two p orbitals of oxygen atoms to make a 2 sigma bond. While other two electrons of carbon atom, what will happen? There are 4 electrons, 2 you have seen. Now other 2 electrons of carbon atoms are involved in pi-pi bonding with oxygen atom. This result in its linear shape with both CO bonds of equal length 115 picometer with no dipole moment. Okay, then here you have seen that 2 sigma bond is formed while other two electrons of carbon atom are involved in pi-pi bonding with oxygen atom. Means linear sigma bond, and this sigma bond as well as pi bond both are present. Two oxygens are there, CO, CO, CO. Then in that two sigma bond and two pi bonds are there. This result in the linear shape. Its shape is linear, a straight line like that, and its bond will be 115 picometer with no dipole moment. The resonance structure you can write, it says resonance structure you can write means there are three structure. Then one time it will form oxygen and carbon single bond, and carbon and other oxygen atom triple bond. That is the one structure, one single and triple bond. C and O with one oxygen single bond and with other oxygen triple bond. Correct? And again another structure, both will have double bond, both side. First with first oxygen also double bond, with second oxygen also double bond. And third structure, with first, third, three carbon, three bond with first oxygen, and with second oxygen single bond, means the reverse of the first structure. Then obviously where three lone pair first with in the first structure three lone pair of oxygen is there, three lone pair of electrons are there on oxygen, then that will be negative, and second oxygen will be positive. Correct? And reverse of this third structure, reverse of first structure is third structure. There again where triple bond is there, then there it will be positive, because only one lone pair of electron is there. When positive, then only one lone pair of electron, and when negative, then three lone pair of electron and oxygen is there. This I have told about the resonance structure of carbon dioxide. Now I am going to discuss silicon dioxide, SiO2, silicon dioxide. This is a very, very important compound of silicon. 95% of the earth crust is made up of silica and silicate. Silicon dioxide, commonly known as silica, SiO2 is known as silica, and silica occurs in several crystallographic form. Quartz, first form is quartz, Quartz, quartz. Second is the cristobalite, second, and third is the tridimite, tridimite. Okay, three structures are there, which is found in three crystallographic forms. First is the quartz, and second is the cristobalite, and third is the tridimite. These are, you can say, forms of silica. And other things I want to tell you, all are these are interconvertible at suitable temperature. All three form, that is a quartz, is convertible to cristobalite, and crystallite it is convertible to tridimite. All are interconvertible, but they are at suitable temperature. Silicon dioxide is covalent. Again, more things you know. Silicon dioxide is a covalent, three-dimensional network solid, in which each silicon atom is covalently bonded in tetrahedral manner to 4 oxygen atoms. Means one silicon is attached to 4 oxygen atom, and with a covalent bond, 4 covalent bond. One silicon is attached with 4 oxygen with covalent bond. Each oxygen atom is in turn covalently bonded to another silicon atoms. Like that way, you can say complete network will be there, big structure will be there. Each oxygen atom in turn or again covalently bonded to another silicon atoms. As a this structure is very like that way, big structure. It will form big structure. And other things, each corner is shared with another tetrahedron. Each corner, if you see the structure, then you will find each corner is shared with another tetrahedron. The entire crystal may be considered as a giant molecule in which 8 member rings are formed with alternate silicon and oxygen atoms. 8 membered ring. Then you will think how 8 membered ring? Then its structure will be just like a square structure. But in this square structure you will find that in a square 4 corners will be there. Then each corner one silicon will be there, and between the 2 silicon oxygen will be there. Then its appearance will be just like a square or 8 membered, because 4 silicon is there and between the 2 silicon 1 oxygen is there. Then a square means they have 4 sides, then each side between the 2 silicon 1 oxygen is there. Then 4 silicon 4 oxygen, on each side 1 oxygen between silicon. Hence like that way many, you can say this square will be there attached to each other. Then that is called 8 membered rings are formed with alternate silicon and oxygen atoms. So many square are attached, and in each square corner 4 silicon, and between the silicon oxygen will be 1 oxygen will be there. 4 oxygen 4 silicon, and it will continue. It will continuously, it will increase everywhere, every side. Then this is called 8 membered ring. Many rings will be attached to each other. Silica in its normal form, it is almost non-reactive. It is a non-reactive. It will not react. Why? Because of very high SiO bond enthalpy. Okay, it is a silicon oxygen, when it forms a bond, that time it releases too much energy. Then to break this bond, it requires very high energy. Normal way it will not react. That's why silica in its normal form is almost non-reactive because of very high SiO bond enthalpy. It resists the attack by halogens. It will not react with halogen, dihydrogen and most of its acid and metals. It will not react. It will not react with halogen. It will not react with hydrogen. It will not react with the most of the acids and metals. Even at elevated temperature, it will not react. That's why it is very, very strong, and its use is more. Its use is more because it is non-reactive and it is very strong. Even at elevated temperature, it will not react. But, or you can tell, however, it is attacked by HF and NOH. Okay, HF and NOH, it will be attacked by hydrogen fluoride and sodium hydroxide. Then SiO2 plus 2NOH, it will give sodium silicate Na2SiO3 plus hydronium ion H3O H plus. Okay, hydronium ion H2O, you can tell H2O Na2SiO3 and it will form H2O. And another example, SiO plus 4HF, hydrogen fluoride, it will form SiF4, SiF4 silicon tetrafluoride plus 2H2O. Okay, then it reacts with NOH and HF, and it will give, with NOH it will give Na2SiO3 plus H2O, and with HF, SiO2 plus 4HF, it will give SiF4 plus 2H2O. Now you can see its use. Quartz is extensively used as a piezoelectric material. Piezoelectric material. It is you can say it has made possible other things. It has made possible to develop these things externally, or you can tell not like this, because it is very hard. Quartz is used as a piezoelectric material. It has made possible to develop extremely accurate clocks. Clock in that it is used. Extremely accurate clock which will give accurate time, because it will not their hands, clock hands will not can say will increase in presence of high temperature. Also their length will not increase. Okay, their hands will be there, clock that will not change with temperature. That's why accurate clock time what will give, that is the accurate. Ordinary watch their time will change in summer and winter, because their length, hand's length will change with temperature, but here hand length will not change with temperature, because it is made from the silicon. These important things I told you. And also in radio, modern radio and television broadcasting and mobile radio communication, it is used. Mobile radio communication, it is used. Silica gel is used as a drying agent, because it will absorb the moisture, and as a support for chromatographic materials, and also it is used in a chromatographic or as a chromatographic material, as a drying agent and as a support for chromatographic materials, and also as a catalyst. One this is there, Kisan-Gur, an amorphous form of silica. What is the Kisan-Gur? KISELGHUR, Kisan-Gur, KIESELGHUR, Kisan-Gur. That is the Kisan-Gur. It is an amorphous form of silica. Is used in filtration plants. Big plants will be there in industry. Then there in that plant, as a filtration plant, this is used. Okay, Kisan-Gur is used in the form of amorphous powder in filtration plants. Now I am going to discuss silicones, not silicon, silicones. SILICONES, silicones. It is actually polymer, inorganic polymer, you can tell. It is inorganic polymer, silicones. SILICONES, silicones. They are a group of organosilicon polymers which have, its formula is a R2SiO. R2SiO. R2 means maybe alkyl group. This is the repeating unit. In polymer, you know that there will be repetition of the unit. Then here repeating unit is R2SiO. The starting material for the manufacture of silicones are alkyl or alkyl or aryl substituted silicon chloride. Okay. Here, a starting material for the manufacture of silicones are alkyl or aryl substituted silicon chlorides. That is the RnSiCl 4 minus N. N is the number. Okay. RnSiCl. Cl, how many molecules of Cl? Then 4 minus N. It depends upon Rn, a small n, where R is a alkyl or aryl group. When methyl chloride reacts with silicon, in the presence of copper as a catalyst at a temperature around 573 Kelvin, various type of methyl substituted chlorosilicon of formula MEsICl3. Three types are, you can say, silicones will be formed. I will tell you one by one. But condition, when methyl chloride reacts with silicon Si in presence of copper as a catalyst and temperature 573 Kelvin. Copper catalyst, temperature 573, then methyl chloride, maybe that methyl chloride may be CH3. Carbon has 4 valency. Then this carbon, out of 4 valency, 3 will be joined with CH3 and 1 with chlorine. This is the one type. It is also called methyl chloride. Okay. And this, when 2, then dimethyl chloride, and 3, then trimethyl chloride. Then here, when 3 type I told you, CH3Cl, CH2Cl2 and CHCl3. 3 types are there methyl chloride. Then according to the types of methyl chloride, it will give 3 types of, you can say, silicon. Then here, that's why it is called substituted chlorosilane. Silane means actually Si, just like a CH4. It is a SiH4. Si, silicon, 4 hydrogen will be attached. Then just like a methane, it is called silane. SILANE, silane. Then 1,1H will substitute with, you can say, these things, methyl group. Methyl H will go and CH3 will be attached. Then 4 CH3 can attached. When all SiH, 4 H is there, all H will be substituted with methyl. Okay, methyl. Hence, it can form a different type of, you can say, substituted chlorosilane. It will form substituted chlorosilane. And formula you can write like this: MEsICl3 means 3 Cl just substituted with 3 hydrogen, and 4th one substituted with methyl. That's why it is called substituted chlorosilane. Okay, methyl substituted chlorosilane. Then first it can form Me means methyl, Me means methyl, or CH3 also you can write, MEsICl3. Now another 2 Me, then 1 chlorine will go, then Me2SiCl2, and third one again Me3, then 1 Cl will be there, total 4, Me3SiCl. And also you will get with a small quantity of Me4Si. In the place of 4 hydrogen, 4-methyl group will come. Hence, a small quantity of Me4Si is also formed. Hydrolysis of dimethyl dichlorosilane. I told you 4 types of silane it will form. Then in that I am talking about particularly for dimethyl means 2CH3, 2Cl2 is attached with silicon. With silicon 2Cl and 2-methyl group is attached. Then that is called dichlorosilane. The hydrolysis of dimethyl chlorosilane followed by condensation. After the hydrolysis, if will do condensation, then it will polymerize. And what it will form after the polymerization? Then polymerization will take place and it will yield, means it will form a straight chain will be formed, means very simple way, 2C methyl chloride 2CH3Cl plus Si in presence of copper powder at 520 Kelvin, it will form CH3 whole 2 SiCl2. Okay, and again further it will react. If the same situation is there, then CH3 whole 2 SiCl2, further it will continue reaction with the methyl chloride and with water. Hydrolysis means water is presence is required. Then again it will form CH3 whole 2 SiOH whole 2. Okay, it will form with water, means 2 methyl chloride plus Si. It will form CH3 whole 2 SiCl2. On further hydrolysis, means further when this CH3 SiCl2 will react with water H2O, then 2HCl will come out and it will form CH3 whole 2 SiOH whole 2. Okay, this is the you can say main product, and this CH3 whole 2 SiOH whole 2, this product what formed CH3 whole 2 SiOH whole 2, this 2 molecules of this means Si, and with Si3 CH3 is 2 CH3 is attached, up and down CH3 and left side OH and right side OH. Then two molecules, same molecules, 2 molecules they will react because OH in both molecules OH is there. Si upside CH3, down CH3, left side OH, right side OH, same way other molecules. Then both OH are close. Then they will form water, OH plus OH. Then OH plus OH, then H2O it will form, and they will make a link with oxygen, OH and OH. Then OH plus 1H from the other molecule OH. Then it will form H2O, it will go out and oxygen will be come in the middle. They will join by oxygen. Okay, like that way third molecule will be there. Same molecule, third molecule means Si upside CH3, down CH3, left side OH, right side OH for balancing. Then again this OH will react and H2O will go out and oxygen will come in the middle. Hence like that way long chain will be formed. Okay, and this is called polymerization. Then there is no limitation with how many molecules are there. They will be joining with O will come in the middle. Between the 2 molecules they will join with O, always with O, and always it will be repeated. That's why in a general way silicon you can write that Si upside CH3, down CH3, left side O, right side O. Why right side and left side O? Because it has joined with O. Left side also they have joined, right side also they have joined long chain. Hence this Si upside CH3, down CH3, and oxygen also left side, right side, and whole you can write whole n. N may be, n you don't know how many, n may be 10, 15, 20, 100, 200 also. That is the n. And outside also same thing can write Si CH3 up and down CH3, and again O you can write, or don't write, only one line you write. Both sides starting and end time, just to open hand like that you can write, because open hand means it can join with other molecules. Hence in a general way it is written, silicon is written like this: CH3, Si will be in the mid center, upside CH3, downside CH3, left O, right O, and whole n, small n, number, repetition, you don't know how many more these are there. That depends upon how many units are joined. N is the number of unit. Okay. Then again both side it will be open hand, because it can join with other. Then at least one you can write. Then Si, another Si you can write. Si you can write. Then already you know that it is joined with oxygen, and right side it is open, upside CH3, down CH3. This is the, I told you about the silicon. Okay. This is very this is called actually block. The chain length of the polymer can be controlled. How many it will be? If we will not control, then this will continue polymerization. Then that can be controlled by adding CH3 whole 3 SiCl, which blocks the end all are open, both side, left side, right side, then that will be blocked by, if we will use CH3 whole 3, means trimethyl silicon chloride, then it will be, both hand will be blocked. Then this I have told about the silicons being surrounded by non-polar alkyl groups, CH3. These are non-polar. Silicons being surrounded by non-polar alkyl groups are water repelling in nature. It will not phobic, you can say, hydrophobic, water repelling in nature. They have in general high thermal stability, no effect of heat, high dielectric strength, and means will not dissolve, high dielectric strength, and high resistance to oxidation and chemicals, no effect of, you can say, chemicals, no, and resistance to oxidation. It can't react with oxygen also, means it has a very good quality. Okay, very too much quality it has. That's why it have several use. They have wide application. They are used as a sealant, sealant, grease, electric insulator, as electric insulator, and for waterproofing of fabrics, waterproof. It is used as a waterproofing materials or fabrics. Being you can say this thing biocompatible, they are also used in surgical and cosmetic plants. Now, in the end, I will discuss about the two things, silicate and zeolite. A large number of silicates minerals exist in the nature. Some of the examples are feldspar. Feldspar is silicate. Other example is zeolite. Third example is mica. Fourth example is asbestos. The basic structure unit of silicate is SiO4. SiO4 4-, in which silicon atom is bonded to 4 oxygen atoms in tetrahedron fashion. Means Si will be in the middle and 4 it is joined with 4 oxygen in tetrahedron fashion. In silicate, either the discrete unit of is present or a number of such units are joined together. All silicate SiO4 will be joined to each other. Okay. When silicate units are linked together, they form chain ring. Already I discussed same type of ring. They form just like SiO2, SiO4 also they will make chain. They form chain ring. Ring sit or 3-dimensional structure. It will form a 3-dimensional structure. Length, breadth, height means thickness will be there. Negative charge on silicate structure. Negative charge on silicate structure is neutralized by positively charged metal ions. Whenever silicate will be there, silicate is negative, then metal ion is positive, they will join and charge will be neutralized. Okay. Then this I have told you about the distance for a silicate. It is a 3-dimensional network. It is a big, it can form big molecules also, large molecules, giant molecules. Now, 2 important man-made silicate are example of silicate man-made, not natural, man-made. That is the glass and cement. Glass and cement. In glass also a silicate is used and in cement also silicate is used. Now come to the zeolite. Already I told you in the previous chapters. Again I am telling you what is the zeolite. If aluminum atoms replace few silicon atoms in the place of silicon, few, not all. If aluminum atoms replace few silicon atoms in 3-dimensional network of silicon dioxide, I told you that silicon dioxide, they are forming 8 means there is a chain. That is the 8 members are there, 8 members chain. Then in that only, suppose some aluminum is coming in the place of silicon, in silicon dioxide, then overall structure is known as aluminosilicate. Okay, in the place of, in some place of silicon, aluminum will come, then it will be called aluminosilicate, acquiring a negative charge. It will be negative charge, then cation will be metal. Negative charge, then cation will be metal ion. Then cations such as sodium ion, potassium ion, calcium ion balance the negative charge. Examples are feldspar and zeolite. Zeolite anion, that is negative charge. And when this sodium, potassium, calcium will join, which is a positive charge, cation, then they will be neutralized. Then examples are feldspar and zeolite. Zeolites are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons. It is used in industries for cracking hydrocarbons. And isomerization. Isomerization also it is used. And example of this I am telling you for these things, isomerization, ZSM, capital Z, S and M5. This is actually a zeolite example, one type of zeolite. Capital Z, capital S, capital M5. It is a type of zeolite. And it is used to convert alcohols directly into gasoline, means petrol. This zeolite used to convert alcohol directly into gasoline. Hydrated zeolite are used as ion exchanger in a softening of hard water in filter. Zeolite is used. Hydrated zeolites are used as a ion exchanger in a softening of hard water. Now I am stopping only here. Today I have finished P block elements. Okay, means this in P block elements we have discussed 13 and 14. Okay, rest it will be discussed in the higher classes. Okay, next class we will discuss new chapter. Thank you.